Assalamu alaikum everyone. So this is the fifth lecture of the course Wireless Networks, and the topic for this lecture is wireless sensor networks. So in this lecture I'm going to give you an introduction, or sort of like an overview, on different kinds of wireless sensor networks and how wireless sensor networks work. So first of all, what is a wireless sensor network? A wireless sensor network is a wireless network consisting of spatially distributed autonomous devices using sensors to cooperatively monitor physical or environmental conditions such as temperature, sound, vibration, pressure, motion, or pollutants at different locations. So the first part is wireless sensor network is a wireless network, right, consisting of spatially distributed autonomous devices. So this means spatially comes from the word space. So this means that the devices are distributed throughout the space or throughout the area, and they're autonomous devices, which means they can think for themselves and they are self-organizing and stuff like that, and it using sensors to cooperatively monitor physical or environmental conditions. Okay, so this part is important because it says specifically that the sensors cooperatively monitor, okay, not one alone, but they if you get the readings of all the nodes together, then you get the total picture. So this is what it means to use sensors to cooperatively monitor. And then the part which says that physical or environmental conditions. So these are just the examples of the stimulus that the readings can have. For example, it can be temperature, sound, vibration, pressure, motion, or pollutants at any different locations in that specific area where the wireless sensor node is deployed or wireless sensor network is deployed. So what does a wireless sensor network contain? So it basically contains of two things. One is the base station, which collects all the information and all the reading, and the base station usually has much more processing power compared to the devices. And the second thing is this several wireless sensor nodes, okay, or wireless sensors. So this figure here is an example. So as you can see, the red marked things you can say is producing some sort of stimulus, and the blue boxes, they are actually the wireless sensor nodes, and they are collecting this information. So although it's written here that it's actually reading sound, heat, target, vibration, etc. but usually there is a specific functionality to the wireless sensor network. So as you can see, there is another device without the sensor nodes, which is the sink, and the sink is connected to the internet, and the internet is connected to the user. So basically the base station here is including both the sink and the user, and the user has much more processing power compared to the sensor nodes, and it is the job of the user to analyze those readings and determine or come to a conclusion based on those readings. So from this structure you can easily understand that the user can be far away from the wireless sensor network, as the user can be connected to the sink using the internet. So as you have already seen, a wireless sensor network consists of a large amount of sensor nodes. So it's usually much more compared to other wireless networks, and the data has to communicate in multi-hop patterns. That means usually it's not that the source and destination are in one hop distance, because most of the in most of the cases the destination is usually the user or the base station. So every node has to communicate with the base station, and obviously it contains wireless communication, because the wireless sensor networks are usually deployed in places where it is difficult to contain wires or keep a wired connection between the devices. And it has cooperative sensing, collection, and processing, which means the entire sensor network works like a unit. It senses different things from different areas. That means if there are, for example, 5 devices throughout the area, then each device has their specific readings, and then all of those readings are combined together and then made let's say summary of that data, and then it's sent to the base station, okay, and then the base station does the processing. And you can also say that there's a minimum amount of processing in the wireless sensor nodes, because they have to compress the data. And wireless sensor networks are used to monitor the environment or system by measuring physical parameters such as, for example, temperature, pressure, and humidity. We have already seen this. So these are the basic components of a wireless sensor node or a wireless sensor device. Okay, so as you can see, there are different boxes here. The boxes which have thick line, that means not dotted, just straight thick lines, those are the parts or components of the wireless sensor network node which are required. That means they must be present. And those boxes which have dotted lines, they are the ones which can be present or which cannot be present. Okay, so first of all, I'm going to talk about the must be present components. So the first thing is powered unit. Obviously, then there has to be a battery which gives power to the device so that the device can process or do whatever it needs to do. And there will be a sensing unit. So the sensing unit can contain a sensor to sense any temperature or heat, etc. And it needs to contain an ADC or analog to digital converter, because the senses or the readings that you get, they are actually analog, right? For example, heat, it's an analog value, and then temperature, that's also temperature. Okay, they're the same thing. Humidity or maybe sound, all of these are analog values, and when you are working with data, you are actually working with digital values. So there needs to be an analog to digital converter which converts those analog things to digital data. So that's the sensing unit. And then we have the processing unit. So the processing unit contains two things, which is the processor and the storage, typical to any sort of processing device, because it has to process the data and it has to store the data somewhere so that it can fetch and process when required. So this is the processing unit. And then is the transceiver unit, which is basically used to send or receive data. So these four things are the most important, and they are the must be components of a wireless sensor node: the power unit, sensing unit, processing unit, and the transceiver unit. So now let's talk about those which can be present or cannot be present. For example, the power generator. So there can be a power generator because the devices are usually deployed in areas where you cannot recharge those batteries. So there can be a power generator which automatically recharges those batteries. For example, it can be solar powered, or if it's deployed in a volcano, for example, it can be charged based on heat. So these sort of things can be used. And then we have a location finding system. So this is sort of like a GPS. So this is also not a must be component, but it can be present. For example, when you are monitoring a traffic area, or for example when the network is deployed in vehicles. So the devices can be in vehicles roaming throughout the country or throughout an area. In that case, you have to also read where the devices are. So there can be a location finding system. And then another component is a mobilizer. So what does the mobilizer do? For example, I think I've already told you about the movie Twister, right? So if you have seen the movie, then you will see that the devices which are used to actually monitor the cyclone or in the inside of a cyclone or twister, first of all, when they were used, the twister used to collect those devices but throw them out of the cyclone. That means the devices could not stay in the cyclone for a long enough time so that the readings can be taken. But afterwards, wings like flaps were connected to those devices so that they can fly, or the wind can take them up, and they could stay inside the cyclone for a long amount of time in that way. So these wings or flaps that were attached, so these sort of things can be attached to the devices so that they can have mobility. Okay, and then maybe even wheels can be attached to some devices so that they can move on the ground if required. So these are the things, or these are the components which provide mobility to the sensor nodes. So before we go into the details of a wireless sensor node or sensor network, at first let's see what an ad hoc wireless network is. Okay, so I think I've already given you a brief overview. So what wireless ad hoc networks are. So these networks usually contain a large number of self-organizing static or mobile nodes that are usually deployed in a random way. Okay, so they have to be large in number and they have to be self-organizing. That means no one will come to place them in certain places, or maybe configure them, or maybe tell them where to send data. They have to do that by themselves. and the nodes can be static or mobile, and they're usually deployed in a randomized way. That means they're usually deployed in a random area. Okay, for example, the area of those nodes does not have to be fixed. Then the next thing is they usually communicate with the nearest neighbor. Okay, they do not send data directly to someone far away, even if they have the capacity to do so. And obviously the connections have to be wireless. The links links are usually fragile. That means the links can easily be broken down, or there might be failure easily, and the links are possibly asymmetric. So asymmetric means when there's a bidirectional link, it means that data can travel both ways, from source to destination or from destination to source. And asymmetric means these two data rates, that means from source to destination and destination source, these two data rates can does not have to be same, so they can be different. This means asymmetric link. Okay, so this is called an asymmetric link, and the connectivity depends on power levels and fading. So obviously they're usually deployed in areas where there can be a lot of interference and where there are no people to actually configure them. So the connectivity depends solely on their power levels, the amount of power they have, because the higher power level they have, the more powerful the signal can be that they sent as a message. And as the signal becomes more powerful, there is less chance of data loss. Another important thing is fading. So due to the different environment and due to the various interference or noises present in the environment, or maybe some physical obstructions present or obstacles present in that area, fading is also an important thing when sending those messages. And next is interference. As I already said, interference are high, but even then it's higher when the antenna is unidirectional. So most antennas are omnidirectional, but in case of wireless sensor nodes, as you have less power, you cannot send data, or you cannot send signals in all the directions, because that will consume a lot of power. So usually they have unidirectional antenna, and which is why the interference is also very high, because it only travels in one direction. Examples of ad hoc wireless networks are sensor networks and sensor actuator networks. Okay, so as we can already see, wireless networks are also an example of ad hoc networks. So now, as we have seen the generalized characteristics of ad hoc networks, we can go, or we can dive deeper into wireless sensor networks. So wireless sensor networks have a few characteristics or properties of their own. So usually wireless sensor networks are very small in size. Nodes are very small in size, and there are a huge number of nodes, and tetherless means there is no wire in between them, and they have to be low cost. It means the production cost of those sensor nodes has to be very low. And there are many constraints in wireless sensor networks, including energy, computation, and communication. So there is very less power or very less energy, and obviously as there is less energy, there is less power for computation. So the sensor nodes do not have a higher computational power in order so that they do not consume much power, much energy. And also the communication has low signal power, so you cannot send a message to a faraway node. It has to be nearest neighbor communication. So the small size of the sensor nodes implies that the battery is also small, which means you have less power compared to other wireless networks. And as there is low cost and low energy due to a small battery size, it also means that you have low CPU power, or low processing power, and low radio signal power. So if you have low radio signal power, that means you cannot communicate to a faraway node, as I've already mentioned. And there is also minimum bandwidth and range. So the range has been covered, but why is there minimum bandwidth? Because usually the area where sensor networks or nodes are deployed, there is a lot of interference and noise, and so and they might also be deployed in an area where local area networks might be present, which is why they have minimum bandwidth and they have to work with that minimum bandwidth. And another reason is, as a huge number of sensor nodes are deployed in the same area, they have to work with the bandwidth given to them. So compared to the bandwidth, there are a huge number of nodes. The next is ad hoc deployment. So as we've already seen what ad hoc networks are, we know what ad hoc deployment means now, right? So as the deployment is ad hoc, it implies that there is no maintenance or no battery replacement. So no person can go to that area and fix those nodes or maybe change the battery. So to increase the network lifetime of those devices, no raw data is transmitted. So what does raw data mean? So raw data means whenever you're reading a temperature in a sensor node, do not send it directly. That's what the sensor nodes do, because if they send data all the time, then their lifetime will decrease very quickly, which is why they have to stay patiently and read the data, and when you have to send it, maybe they send the data periodically, so they have to compress the data as well. So this compression means that there is no raw data transmitted. For example, if a sensor node is deployed in a volcano to get the temperature reading, so if it sends the temperature in every second, that means that you have to send data for 24 into 3600. So that's a huge number of seconds, right? Compared to that, what it can do is it reads the temperature for the entire day and maybe does an average and only sends the data once per day. So that's a huge increase of lifetime for the sensor node. So wireless sensor nodes can be deployed in extreme environmental conditions, as I've already said, and may be also prone to enemy attacks. So enemy attacks can include other animals, or it can also include people, because there are also military uses of sensor networks. So although deployed in an ad hoc manner, they need to be self-organizing and self-healing and can face constant reconfiguration. Okay, so they have to be self-organizing. That means they have to configure their routing, they have to configure or they have to fix their link failures by themselves, and they have to be self-healing. So which means that if they die or if they lose battery power, then that's that. So they have to have a mechanism so that they can again maybe increase their battery life using, let's say, a power generator, or so that they can understand that there's a link failure and automatically heal their network. And they have to be able to face constant reconfiguration. So this does not mean that the people has to, or the person has to go and configure those devices. No, this means that the configuration done from a distant place. So the configuration commands may be given to wireless communication, and those networks have to configure themselves based on those commands. So the things that we have seen till now are the specific characteristics of an ad hoc network and a wireless sensor network. So now we are going to see the differences between the ad hoc network and wireless sensor network, and what makes wireless sensor network unique compared to the other ad hoc networks. So wireless sensors are ad hoc networks, obviously, because the wireless nodes are self-organizing, and also they do not have an infrastructure. That means they do not have a hierarchy. So there is no access point, or there is no node which has more power or more authority compared to the other nodes. All the nodes are equal. However, they are quite different compared to other ad hoc networks in the following ways. For example, sending and data processing is essential. In case of the other nodes or other networks, they do not have to process the data. They can automatically send the data whenever they have to. But in this case, they have to sense, which is much more important, and sensing is not present in the other networks, and they have to also process the data. So these two things are essential if you are talking about wireless sensor network compared to other ad hoc networks. And they have many more nodes compared to other ad hoc networks, and they are usually deployed in a very dense way, so that they can communicate easily with each other, with the nearest neighbors, without much power consumption. And the hardware needs to be cheap, and they are usually prone to failure, because obviously they are deployed in places where they can be easily destroyed. So it's no use creating nodes which are very expensive. The nodes have to be very cheap so that they can be discarded whenever required, so that even a few of them gets destroyed, it's not a problem. You can just create more and then send them there again. So the hardware needs to be cheap, and they can be prone to failure because they are cheap. So they operate under very strict energy constraints. So that means in case of other ad hoc networks, they're not much energy constrained, so they can use energy as much as required. But in case of wireless sensor networks, that's not the case. You have to be very careful of your energy, and usually it's very static, unless it's in a twister, as the example as I've already given. So except those cases, the network or the nodes are usually static in a specific place. So as I've already said, the mobilizer part of the component, if you remember, right? So this mobilizer, it's not a compulsory thing, so it can be present and it cannot be present. So it's only present in the cases when the network is not static. Otherwise, if it's static, then a mobilizer will not be present. So communication is many to one, which means the nodes do not communicate with each other. Okay, they do communicate with each other to some extent, but their main target or main destination is the sink or the base station. Okay, so this means the communication is many to one instead of peer to peer. So peer to peer means my source and destination are in the same network, but in case of many to one, it means all the nodes of the sensor network communicate with the base station. So their initial their end target is the base station. So the nodes do not have global IP, or as you already know, most of the nodes in a wireless or wired network have an IP address, right? But these nodes do not have IP address because they are very huge in quantity, and there is a huge amount of overhead. So, but what does global IP mean? So does this mean they do not have any IP at all? No, they have an IP address, but that's not related to the global address, because as there are a huge number of nodes, if you actually give a global IP address to every node, then you will run out of IP addresses, which is why they do not have a global IP address, but they do have a local address which is used to communicate with the base station. Because without any address, you cannot specify to whom you are sending a message. So they do have a local IP address, but they do not have any global IP address. So they do not affect the total number of IP addresses that are present globally. Okay, so these are some of the challenges that we face when working with wireless sensor networks. So the first one is energy efficiency. As we have already said, you have to be very efficient with your energy, and the nodes have limited storage and computational power. The bandwidth is very low, and the error rates are very high because of wireless communication, as wireless communications has higher error rates compared to wired communication. And obviously, as the environment is very noisy, the measurements can be very different from the original ones, which is why the error rates also increase. And obviously, due to failure of nodes, which is also expected in case of wireless sensor nodes or wireless sensor networks, and the error rates also increase. So as you can clearly see, wireless sensor networks have many challenges compared to other networks. And scalability is also an important thing, because scalability means to be able to adapt to the change in size of the network. So the network size can increase or decrease. So based on that, your network needs to be able to manage this change. So this is called scalability. And as there is a large number of sensor nodes, scalability is also important for wireless sensor networks. And next is survivability in harsh environments. So the devices have to be created so that it's sturdy, so that it is able to at least be alive for a specific amount of time in that harsh environment. For example, if you deploy a node in a volcano, it has to be enough heat resistant so that it can survive that environment. And if you send it inside a tornado or twister, for example, it has to be strong enough so that even if it hits any other item or objects that's inside the twister, or even in that high pressure environment, it has to be able to survive it. So the experiments are time and space intensive. So this means that they have to send the data, or they need to be able to send the data when required, so that you get real-time data when you want to access that data. So this means time intensive. And space intensive means when they are deployed in a specific area, they have to give you the data of that specific area. So the time and space of those data that you get from sensor networks, sensor nodes, they are very important. You have to get the data of a specific space or specific area, and also at the given specific time, so the message cannot be delayed, because applications of wireless sensor networks are usually in places where getting the data in real time is very important. So the lifetime, as I've already said, the power of those devices is very important, because there is no one there to replace those batteries, and the nodes are battery powered, obviously. So as no one is there to replace those batteries, or no one can go to that harsh environment to replace the batteries, so each operation or each data sent or each processing done brings the node closer and closer to death, because that battery life is all it has, and once the battery is gone, battery life is gone, no one will go there to even change the nodes. All the people can do in wireless sensor networks or in harsh environments is deploy more nodes. So lifetime is very crucial, and it is very important to save the energy. So the node has to sleep as much as possible. Whenever you do not have to send data or maybe sense data, or whenever you have time, you have to sleep to save the battery life. And the nodes have to acquire data only if it is very, very important. Otherwise, you do not have to acquire data. And also transmit or receive data only when necessary. So you might be thinking that, okay, transmitting consumes a large amount of battery power, right? But receiving should not. Well, actually, that's not the case. Transmitting and receiving both are almost equally costly in terms of battery power. So how do we reduce the battery? How do we increase the battery life, or how do we improve lifetime? So these are some of the things that we can do, or some of the approaches that we can take. The first one is reducing the amount of data traffic. So how can we reduce the amount of data traffic? We can predict or forecast data trend. For example, if we know that these devices are deployed in a volcano, and we know that during this time only we need to read the data, because this is the time throughout the year or maybe throughout the month, this is the time when something might happen, or this is the time when we have to get the reading. If we somehow know that time, then we can forecast, okay, so we have to only be present, or we only have to be alive during that time. The rest of the time we can sleep. So this is one way to reduce the amount of data traffic. And the second is model-based solution. So what we can do is we can assign a model for the network so that it reads data for a specific amount of time, even if we do not know that whether that time is important or not. But we can still say that, okay, instead of sending data all the time, maybe send the data and sends the data after every 1 hour. So this means that we are specifically saying that during that 1 hour we are not taking a reading, and all this is the loss, because something might happen during that 1 hour as well. But this is a risk we have to take, so that the sensor network can at least be alive for more time compared to before. So the next approach that we can take is data fusion or compression. So what we can do is, instead of sending a data all the time, we can compress the data. I've already mentioned an example. For example, I think I mentioned average. So instead of sending the data all the time, you can average the data for the entire day and then send it, or maybe average the data for 1 hour or 2 hours or 3 hours or so on. And without averaging, there are also many other techniques which can be used to compress the data. Next is, so before going there, if you know, we already have many compression techniques which compress an image, right? So using those techniques, the same amount of data without any loss can also be sent. And next is optimized wake up interval. So this means that instead of waking up all the time, so waking up means waking up from a sleeping state of our sensor node. So optimized wake up interval means that the amount of time that you stay awake and the amount of time you sleep, if it is optimized in a way so that you sleep more and stay awake less, so that will also improve your lifetime. Next is optimized beacon interval. So usually in a wireless sensor network, there are beacons. Okay, so beacons indicate that, okay, now I have woken up from sleep and now you can send me a data. Okay, so we're going to learn more about beacons in the protocols related to wireless sensor networks and wireless LAN. So if the nodes usually send beacon whenever they wake up. So if you can optimize the time when the beacon is sent, and if we know that when the other nodes will wake up, if we know that beforehand, then we do not have to stay awake for the entire time, or we can even optimize our lifetime more, or we can sleep more. So the next approach is reducing the probability of false wake up. So false wake up is when you wake up and you assume that the other nodes have also woken up, or you assume that now you have to actually sense the data, but actually it's not the case. So this is a false wake up. You wake up when you do not have to wake up. So reducing the probability of false wake up also improves the lifetime. And the last is correctly identify the cause of packet loss. So whenever there's a packet loss, you have to send a transmission or a message again. So in case of other wireless networks, that's not a problem, right? The more important thing is to send the data accurately. But in this case, resending is also a problem. So because sending and receiving is so costly, sending a data twice is much more lethal when you are talking about the battery life. So it is very important to detect faulty link before sending data. So if you can detect that, then even if there's a faulty link, you will not waste your energy sending data there. And also use of optimized routing can reduce the amount of packet loss or data loss. Okay, so let's have a look at different design factors next. So these factors determine what we have to take into consideration when we are creating a wireless sensor network. So the first thing is scalability. I have already mentioned what scalability is. The second thing is fault tolerance. So the network has to be placed in such a way so that it can tolerate fault to some extent. So even if there's a link failure, it can manage it and send data to another route. Next is power consumption. So we also have to consider power consumption. For example, if we create the network in such a way that there is a bridge in the network and one node is in the middle of that bridge. So a bridge means that for communication between one part of the network and another part of the network, only one node is present in between. So this means that communication between these parts of the network goes to this one node, which is why it consumes a huge amount of power, right? So if we create and that node will die out eventually, and when that node dies, the communication between the two parts of the network ceases, right? And they cannot communicate. So if this is an example of how we cannot place a network. So we have to place the network in such a way that there is no extra pressure on any node. So based on these design factors, there are two different types of architectures using which actually the sensor networks are deployed. The first one is a layered architecture, and the second one is a clustered architecture, and we're going to see them in brief. So the first one, layered architecture. So if you can see the figure at the left, this is how the layered architecture is actually deployed. So as you can see, the small black dots are the sensor nodes, and the BS is the base station, and the circles that you can see, the large circles, they are actually the hops. Okay, so let me show you. So this is the first hop, this is the second hop, and this is the third hop. So what does the first hop, second hop, and third hop mean? This means that any node inside the one hop layer can communicate with the base station using only one transmission or one hop, and every node in the two hop layer, they need to communicate with the base station with two transmissions. That means one from the two hop layer to the one hop layer, and another from one hop layer to the base station. So similarly, the three hop layers, the nodes in the three hop layer can communicate with the base station using three hop or three transmissions. Okay, so there is a single powerful base station in the middle. So this base station can send data to any hop in any layer. Okay, so that's not a problem for the base station, but the sensor nodes can only send data to the neighboring node. Okay, so all nodes are actually I hop away from the base station, and this I hop is 1 for one hop layer, 2 for two hop layer, and 3 for three hop layer, and so on. Okay, so applications of this layered architecture include buildings, because usually in buildings you can actually have a BS tower in the middle of a building. So in that case, the BTS tower is actually not a tower but an access point, which much more processing power and much more signal power compared to the other wireless nodes. And other applications include in military purposes, for example monitoring the enemy or maybe tracking the enemy. And advantages of this sort of architecture is the nodes has to communicate in short distance, which is why the transmissions can be of low power, and as low power consumption is included here, the battery life is improved much more. The second type of architecture is a clustered architecture. So in this architecture, as you can see, the sensor networks or nodes are actually divided into specific clusters, okay? And those clusters send data to one common node within that cluster, and that common node is called a cluster head, and that cluster head sends data to the base station, okay? So the base station can send data to any cluster easily because of high signal power, but if all the nodes in all the clusters send data directly to the base station, then they will decrease their lifetime significantly, which is why they send data only to the cluster head, and only the cluster head has to be sacrificed in this case, so that the data of the entire cluster can be sent to the base station, okay? And the cluster heads might change after a specific amount of period, so that even the cluster head can stay alive for a long amount of time. So this architecture, as I said, organizes the sensor nodes into clusters, and each cluster is governed by the cluster head, which communicates with the base station, and only the heads send a message to the base station, okay? So next, the design factor which comes next after architecture is data collection, okay? So the centralized data collection puts extra burden on nodes close to the base station, because if you go back, for example in this case, so okay, let me just turn on the laser pointer. Okay, so here if you can see this 3-hop layer, right, they have to only send their message to the base station, right? But the 2-hop layer, the nodes in the 2-hop layer have to send their own message and also the message received from the 3rd-hop layer. And the 1-hop layer, they have to send the message of the 2-hop layer, the 3-hop layer, and also their own message. So the further you go, the deeper you go or nearer you go to the base station, the more pressure is there for the sensor node. So this is what this means, that centralized data collection puts extra burden on nodes close to the base station. So clever routing can alleviate that problem. So a routing may be created which puts less pressure on the closer nodes. For example, the duty of the closer nodes might be alternated between the devices. Next is clustering. So the data from groups of nodes are fused before being transmitted, so that fewer transmissions are needed. So this is one of the benefits of clustering a node, clustering a group of nodes. So if there is one cluster head, then obviously that cluster head has to send data, and all the nodes in that cluster can be safe in terms of battery power. So often getting measurements from particular area is more important than getting data from each node. So using this information, because for example if you deploy, I'm giving the same example again and again, if you deploy many nodes in a volcano, you do not need the data or temperature of every specific point of volcano, right? What you need is an overall temperature reading. So if that overall temperature reading exceeds the threshold, that means it's now in danger or the volcano might erupt, right? So when this is the case, you do not need data from a specific area but an overall data. So using this information we can employ or deploy routing protocols, so that all the time the nodes do not send data, and they send data collectively using one node, which will actually increase the lifetime of the batteries even more. So security and authenticity should also be guaranteed. This is important also when however the CPUs of the sensing nodes cannot handle fancy encryption schemes. So as you can understand, we have low processing power, but even then we have to employ some sort of security or authenticity measures so that the data is protected, okay? So these are the different data collection points that we need to consider when we're designing a wireless sensor network. So next the topic is a power supply. So these are the power supply conditions or facts that we need to consider when we are designing a network. So battery powers the vast majority of existing platforms in terms of wireless sensor network. So they determine the size of the majority of the nodes, obviously. So in most wireless sensor networks, the battery is present, and it's usually battery powered. Okay, as they're battery powered, the size of the battery is what determines the size of the node, because most of the other things, the sensing components or the transceiver or the processor, they are usually very small in size. The battery is the only thing which is large, and based on the size of the battery, for example, if you need a higher amount of battery for a higher lifetime or for a large amount of lifetime, then the sensor nodes also have to be huge. So alkaline batteries offer a higher energy density at a cheap price, but their discharge curve is far from flat, which means they do not provide a flat level of energy. For example, they might provide 3 volt now, 5 minutes later they might provide 5 volt, then 3 minutes later they might provide 4 volts, and so on. So they do not have a flat discharge curve. So this means that the sensor nodes cannot work properly using that battery, but it has a huge amount of battery life, and also it's cheaper in price. Compared to that, lithium coin cells are more compact and boast a flat discharge curve. That means they can flatly discharge for 5 volts throughout their battery life, but they are more costly. So what about rechargeable batteries, right? Rechargeable batteries can be used so that the battery life is improved, but who does the recharging? No one can go there and recharge those batteries themselves. Okay, so an option for rechargeable batteries can include solar cells, so that they can actually collect energy from the sun instead of someone else going there. And fuel cells may also be an alternative, but in the future. So they're not used yet, or any process have not been developed yet which can use fuel cells. So energy scavenging techniques are also a hot research topic. So energy scavenging techniques mean collecting energy from the environment, for example, mechanical energy, thermodynamical energy, or electromagnetic energy, and so on. So these are some of the applications of wireless sensor networks. The first is constant monitoring and detection of specific events. So these events can be anything, starting from natural events to maybe man-made artificial events, and then it can be applications also include military and battlefield surveillance, as we have already said before. So because it's a very dangerous environment in a battlefield, we can use sensor networks, we can deploy sensor networks there. For example, the drones that you see, the drones that the military use, or collection of drones that they use, okay, that can also be considered as a wireless sensor network, because they are just basically sensing or seeing the battlefield and then reporting that to a central base station. Then forest fire and flood detection. So sensor networks can also be deployed in forests or any other area to detect fires and floods. And it can also be used in habitat exploration of animals, patient monitoring, home appliances, etc. So there are many applications. We are going to see some of them. So this is an example of a wireless sensor network deployed by the University of California, Berkeley, and combined with the College of the Atlantic. So it is deployed in the Great Duck Island. The sensor network contains 150 sensing nodes deployed throughout the island, which relay data, temperature, pressure, and humidity to a central device. So this data was made available on the internet through a satellite link. So as you can see the figure here, okay. So this is the figure of the island, and these are the number of nodes. Obviously all the nodes are not depicted here, and so this is a picture of one sensor node in that island, and this sensor node sends the data to a base station. As you can see, the base station is that lighthouse, which has a higher amount of signal power and battery life compared to the sensor nodes. Or they don't have to have battery, they can be directly connected to electricity, and then that sends the data through the internet or through satellite to anyone using an internet, right? So this is the perfect example of wireless sensor node from a distant area. So anyone can use that data, and this was mainly created for academic purposes. So this is another application of wireless sensor network, the Zebranet. Okay, so this is the wireless sensor network to study the behavior of zebras. Special GPS equipped collars were attached to zebras on their necks, and those devices sent data. So for example, this sensor node sends data to the next zebra sensor node and to the next one, and so on, and then eventually it sends data to the computer, okay, or the base station. So in this case, the base station is the computer. So data is exchanged with peer-to-peer info swaps. So this means that the data from this node can be sent here, and this computer can collect the data of all the zebras or all the sensor nodes from this particular zebra. Okay, so coming up across a few zebras gives access to the entire network. So it doesn't have to be this zebra. You can also go near to maybe that one and collect data from the entire network in that way also. So this is another application of wireless sensor network. Intel deployed a 130 node network to monitor the activity of residents in an elder care facility. So activity means what they're doing, what is their current heart rate, and so on. So patient data is acquired with wearable sensor nodes, which is the watches. Okay, so the figure is given here. This is the watch, and the functionalities that this watch includes are vital sign monitoring. So vital sign means, you know, heart rate, blood pressure, etc., and accident recognition. So this means whether they're suddenly in trouble or not, in terms of medical trouble or also in terms of physical trouble, for example falling from a stairs and so on, and also for monitoring the elderly for what they're doing in a specific time. Okay, so the base station, as you can see here, is sort of like a PDA or a device, and so this information is collected in this device, and this device might be connected to the internet. In this way, the information of the entire network can be collected. So as we have seen some examples of wireless sensor networks, let us see how these applications can be divided. So they can be divided into three categories. One is monitoring specific objects, second is monitoring an entire area instead of specific objects, and third is monitoring both area and object. So these are the examples of monitoring an area. So environmental and habitat monitoring. This is related to an entire area instead of an object, because we are actually monitoring an entire habitat. So an example can be the Zebranet that we saw. Then precision agriculture, indoor climate control, military surveillance, treaty verification, intelligent arms, and so on. We're going to see one or two examples from this also. So this is the first example, which is precision agriculture. What does precision agriculture mean? So this aims at making operations more efficient while reducing the environmental impact. For example, maybe you can detect the humidity of the air and then determine whether you have to give water to that plant or not, and you can also detect if there is much heat or if the temperature is too high, then you have to create a cold environment, and so on. So this information is collected from sensors, is used to evaluate the optimum sowing density. That means the distance between the plants that you have sown. Then estimate the fertilizer, the amount of fertilizer that you need to deploy, and other input needs to more accurately predict crop yields. Okay, so they can be deployed to sense that these temperatures are more adequate, or these temperatures are optimum for this plant, and then that temperature can be employed so that the plant can thrive more. So they can also be used in greenhouses. So the next is monitoring objects. Okay, previously what we saw was examples of monitoring areas. So now we are seeing at examples of monitoring objects. So examples can be in structural monitoring, ecophysiology, then condition-based maintenance, medical diagnostics, and urban terrain mapping. And we're going to see some examples of monitoring objects as well. So the first one is condition-based maintenance. So this means that based on what the manufacturing plant is doing and what it is doing and when it is doing, you can monitor what they're doing, and based on that you can change the environment so that you can create in a more efficient way. For example, Intel fabrication plants. So there is a fabrication plant of Intel which manufacture many things, for example chips, microprocessors, etc.
So sensors collect vibration data, monitor wear and tear. That means whether the machines that are producing this, whether they are working properly or not, or whether they're going through a malfunction or not, and then the sensors can report that data in real time, so that less amount of wastage is done. For example, if a machine is not working properly, then maybe the devices that it's creating is faulty, but there is an amount of resource that is used to create those chips, right? So those resources are now wasted. So to reduce that wastage, a wireless sensor network can be deployed so that it can detect just when the device has started malfunctioning, and then the engineers can automatically or immediately go there and fix that device. So this reduces the need for a team of engineers, so that engineers do not have to monitor the devices themselves, and so this cuts costs and other expensiveness by several orders of magnitude. So this was an example of monitoring an object instead of an area. So next we're going to see an example examples of monitoring both area and objects together. So wildlife habitats. So in case of wildlife habitats, you have to actually monitor the health of the animal as well as the environment or the ecology. So just like that, examples include disaster management, emergency response, then ubiquitous computing, asset tracking, healthcare, manufacturing process flows, and so on. So these are all examples of where you have to monitor both the object and also the area where the object is existing. So the Zebranet project, this is an example of habitat monitoring, as we have already said. Collar mounted sensors monitor zebra movement in Kenya. Okay, so and I think the left is the picture of the team which deployed it in 2004, which is Princeton probably. So these are the future applications of wireless sensor networks. So the first application you can consider is the smart home and or smart office. So these smart homes or smart offices can contain sensors controlling appliances and electrical devices in the house. Then it can include better lighting and heating in office buildings. So the person can actually control the heating and lighting based on wireless sensor networks. So this is a picture of the Pentagon. So the Pentagon is a very modern or sophisticated building or headquarters of the United States of America. So it also contains detention facilities for criminals, and this can be a very good example of a smart office, as the technologies contained inside this specific building is very high tech. So another future application can be in the medical or biomedical sector. So this includes health monitors. So some of these are already there, but not all. For example, glucose level monitoring of the body is already there, and you can monitor that. Then heart rate, cancer detection. Okay, so the heart rate and glucose, they're already there, but cancer detection, this is something which has not yet been produced. So if you have to detect cancer, you have to basically go to a hospital and use very high-end devices. But if a sensor network, a very cheap sensor network can be created, then a person can detect it very easily, because in most cases or in many cases actually the cancer is detected at the very last stage or maybe the terminal stage, and it is very difficult to heal such sort of diseases at the end stage. And then wireless sensor networks can also include solution to problems like various chronic diseases like artificial retina. For example, if you have a problem in your eye and you cannot see, then an artificial retina can be deployed. So why is this a wireless sensor network? Because the retina is something, artificial retina is something which has to sense the light, right? So this can be considered an example of wireless sensor node as well. So other examples of future uses can include cochlear implants and hospital sensors to monitor vital signs and record anomalies, and etc. So industrial and commercial applications can also be present for future uses. For example, numerous industrial and commercial applications, for example, agricultural crop conditions, inventory tracking, in-process parts tracking, RFID theft deterrent, and customer tracing, and so on. So there are many applications for future uses in different sectors. And also in traffic areas for traffic management and monitoring, future cars can use wireless sensors to handle accidents, thefts, and already there are some cars, right, which if you open the car without the keys, then it gives a signal. So but there's still not sensor networks which can detect or handle accidents. So sensors can be embedded in the roads to monitor traffic flows and provide real-time route updates as well. So as you can see, there are a huge number of applications of wireless sensor networks, and although I've talked about a lot of them, it's not possible to consider, or it's not possible to cover all of them. So this is just a brief overview of what wireless sensor networks are and where they can be deployed. And that was it for today's lecture. So if you have any questions, obviously you know where to ask. So with this, I'm going to end today's lecture. Assalamu alaikum everyone.